Today's lecture deals with Cramer's rule. This is one way of solving systems of linear equations where the determinant of the associated matrix is non-zero. The theorem states the following. Let Ax equal to B be a system of n linear equations with n unknowns. It's important to notice that the number of equations equals the number of unknowns. If the determinant of A is different than 0, then the system has a unique solution. And this solution is given by xk, where xk represents the kth component of the solution x, is the determinant of mk over the determinant of A, where mk is the n times n matrix obtained from the matrix A by replacing the column k of A by the column vector B. So you take the column k of A and you replace the whole thing by the vector B, where B represents the vector of on the right side of the system. Now the proof follows as in the following. Because the determinant is different than 0, the matrix is invertible. So the system Ax equals to B has a unique solution, and that solution is given by the inverse of A multiplied by B. Now the way we shall find the components of X is as in the following. We shall construct the matrix xk, which is the n times n matrix obtained from the identity matrix by replacing the kth column by x. So here it is. So xk represents, you take the identity matrix and you take the kth column, this is the kth column, and you replace that by the vector x. Now we notice that the determinant of xk is computable using the cofactor expansion over the kth row. So if somewhere here is the kth row has only one entry which is different than 0, and that's xk. All the other entries are equal to 0. So using that cofactor expansion is xk times the cofactor of xk. So the cofactor means the number of the row plus the number of the column, both of them being equal to k, negative 1 to the power of this sum, times the determinant of the whatever minor you get when you remove the kth row and the kth column, and that's nothing but an identity matrix of dimension n minus 1, whose determinant is of course equal to 1. So everything here is equal to 1 but xk, so little xk, the kth component of the solution, is the determinant of the matrix capital Xk. So in order to compute xk, it suffices to find the determinant of this matrix. Now the way we shall compute the determinant of this matrix is to start from the following relation. A times xk is equal to mk. This relation is not very straightforward, so I'm going to show you how that works. In the particular case, n equals to 2 and k equals to 1. The general case being similar, but it's a lot more laborious. So when n is equal to 2, we have a 2 by 2 matrix, and k is equal to 1. So in that case, I'm interested in multiplying the matrix A, which is A11, A12, and so on, by the matrix M. Actually, I consider k equal to 2 here. So by mk, so xk represents, we replace the second row by x, so k is equal to 2. We multiply the matrix by the way we multiply matrices, and then we use the fact that whatever we get here and there, it's the linear system, the left side of the linear system. So we replace the whole thing by b1 and by b2 respectively, and this matrix is nothing but m2, which means the matrix A, where we replace the second row by the column vector b. So taking the determinant in this relation, so this relation can be proved in general. Now taking the determinant and using the multiplicativity property of determinants, we obtain the determinant on mk is the determinant of the product between those two matrices, is equal to the product of the determinants of those two matrices, is equal to the determinant of A times the determinant of xk. Determinant of xk is little xk, as we've seen before, and then solving for xk by dividing by the coefficient of xk, which is determinant of A, we obtain the desired formula. Xk is determinant of mk over determinant of A.